Hello everyone, this is Dr. Suleiman Khan and you are watching my YouTube channel The Beauty of Mathematics. In today's lecture, I would like to talk about the Legendre differential equation and general solution of the Legendre differential equation. So first of all, we have to define the Legendre differential equation. Legendre differential equation. So an equation of the form 1 minus x square double derivative of y double dash minus 2 times x first derivative of y plus n into n plus 1 time y is equal to 0. This is equation number 1. This equation is called Legendre differential equation, where this small n is any real number, and in this lecture we will try to solve uh, the general solution of this equation, which can be written in the form y of x is equal to a naught y1x, where a naught is some constant and y1 is one solution, plus a1 y2 of x. This is equation 2. This is the general solution of the Legendre differential equation, where what is y1 and y2? Here a naught and a1 are some arbitrary constants, and where y1 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 can be written in the form 1 minus n into n plus 1 divided by 2 factorial x square into x square plus n minus 2 n into n plus 1 n plus 3 divided by 4 factorial x power 4 plus up to so on, and this is the general term. This is equation 3, and y2 can be written in this form: x minus n minus 1 n plus 2 divided by 3 factorial x power 3 odd power of x n minus 1 n minus 3. The next is n minus 1 n plus 2 n plus 4 divided by 5 factorial x power 5 minus up to so on. This is equation number 4. These are the general solution of the Legendre differential equation, where y1 and y2 are Legendre functions. So while using this Legendre differential equation, we will try to find the general solution of the Legendre differential equation in the form of equation 2, where y1 and y2 are separately defined like in equation 3 and 4. So for the general solution, how we can solve or we can find the general solution of the Legendre differential equation. So general solution of Legendre's differential equation. So we will use the power series method to find the general solution of the Legendre differential equation. So for this, we will let y is equal to summation m is equal to 0 to infinity am, which are the coefficients x power m, be the solution of Legendre differential equation. We suppose that this y is the solution of the Legendre differential equation 1, and as in 1 there are three unknowns. One is y double dash, y dash, and y. So in place of y, we can replace this series, and we will differentiate this. Uh, so taking the first derivative of this series, this can become summation m is equal to 0 to infinity a power m, where x power m, so its derivative will be m time x power m minus 1. This is the first derivative, and y double dash would be the where m is equal to, it will be 1 from 1 to infinity, and for second derivative m is equal to 2 to infinity. am m time m into m minus 1 time x power m minus 2. This is the second derivative. So now we will put the value of y dash, and y double dash in equation 1. So we can get, substituting these values in equation 1, we have 1 minus x square summation m is equal to infinity. This is the value of y double dash, so it can be written as am m time m minus 1 x power m minus 2 minus 2x, and the value of y dash, which is this one, summation m is equal to 1 to infinity m time am x power m minus 1, this plus n into n plus 1, and the value of y, which is m is equal to 0 to infinity am x power m is equal to 0. So this is the now we will simplify this equation, and we can get the equation in the form summation m is equal to 2 to infinity m time m minus 1 am x power m minus 2 minus having some simplification while multiplying these values with the 1 in the upper equation and also with the x square, because here it was 1 minus x square in the left side. So this equation can be reduced to this form: m is equal to 2 to infinity m minus 1 am, where when multiplying x power m minus 1 with 1 it is again the same, while when multiplying x power m minus 2 with x square, so this will be m, only m. And similarly multiplying with this x in the upper equation with the x minus 1, so this can be reduced to the form m is equal to 1 to infinity am m x power m plus the last result, which is n into n plus 1 summation m is equal to 0 to infinity am x power m, which is equal to 0, and this equation is called equation 7. So replacing now here the powers of x are is m x power m minus 2, this is x power m, the others are also x power m, this and this. So we have to replace this m minus 2 by r into the first series, and m by r in the remaining of the equation 7. So while replacing this value m minus 2 by r and in the first series, and only m by r in the remaining series, so to make the power same, so this equation can be reduced to this form: summation r is equal to 0 to infinity, because m minus 2 is equal to r, so r is equal to 0. And here m should be r plus 2, and this m should be m minus 1 should be r plus 1, and this am, so because we have replaced m minus 2 by r in this one, in this series, and in the other remaining, in all of this one, we have replaced m by r only. So this equation can be reduced to this form: ar plus 2 x power r minus summation r is equal to 2 to infinity r into r minus 1, r minus 1 ar x power r minus 2 times summation r is equal to 1 to infinity r ar x power r plus n into n plus 1 summation r is equal to 0 to infinity, and ar x power r equal to 0. So this is equation for example 8. So now we have all the uh, unknown x in the same power, x power r, x power r, x power r in each term. So we can compare the coefficients on both sides now by comparing the coefficient of x power r on both sides of equation 8. So for example, for x power 0, so when r is equal to 0, so this will be x power 0, right? So here when r is 0, so this will be 2, this will be 1, 0 plus 1, this is a 2. So this coefficient will be 2 times, in this expression the coefficient we can get 2 times a 2, and here r is equal to 0, so this expression is whole expression is 0, and here also when r is equal to 0, so this expression is also equal to 0, and here when r is equal to 0, so it will be x power 0 a naught and n into n plus 1. So the whole equation would be this plus n into n plus 1 a naught equal to 0, while the right side is 0, so we can get this equation. And for x power 1, when r is equal to 1, so this will be 3, this will be 2, 3 2 is 6, and a will be a3. So the first expression we can get 6 times a3, and here when r is equal to 1, so this expression is 0, so there will be no term when this minus 2, when r is equal to 1, so minus 2 a1 minus 2 a1, this expression minus 2 a1, and the last one n plus 1 a1 plus n into n plus 1 a1 equal to 0, or we can simplify this or can written in this form as well. 6 times a3 plus this is n plus 1, while taking a 1 common, we can write this is this equation, right? So similarly for x power 1, for x power 2, for x power 3, and so on, and we can continue. For example, for x power r, we can write it as when r is equal to r, so it is r plus 2, r plus 1, so the general terms will be r plus 2, r plus 1, uh, ar plus 2, ar plus 2, and plus the other expression here ar, here ar, ar. These three are the same, so maybe I can take some number common. Here it will be left when r, so it will be r into r minus 1 minus time r into r minus 1, and the other expression should be the other value should be minus 2 times minus 2r, this one, and the final value will be n into n plus n into n plus 1. The final value will be this AR, which is equal to 0. Or simply I can simplify this expression, which is R plus 2, R plus 1, AR plus 2 plus this can be simplified by a little algebraic simplification. So we can get n minus r and n plus r plus 1 ar which is equal to 0. So or, more simply we can get ar plus 2 equal to, while changing this to the right side, this will be negative n minus r n plus r plus 1 ar dividing by r plus 2 r plus 1 on both sides, so we can get r plus 2 r plus 1. This is equation 9. So now we are n is any real number in this equation, as we have already discussed. N is some real number, and the value of r should be like r is equal to 0, 1, 2, 3, and so on. So the formula given in this equation 9 is called a recurrence relation or recursion formula. So we will use this formula later on. Now, as already we have discussed that a naught and a 1 are some arbitrary constants, so then we can get a2 is equal to minus time, while substituting the values of r in the above equation, n plus 1 divided by 2 factorial a naught and a3 should be equal to minus time n minus 1 n plus 2 divided by 3 factorial a1, and a4 will be equal to minus time n minus 2 n plus 3 divided by 4 multiplied by 3 a2. So this can also be simplified to the form n minus 2 n plus 1 n plus 3 divided by 4 factorial n naught, because while putting the value of a2 over here, this one, and a4 can be reduced to this form in short. Similarly, we can get a5 is equal to minus n minus 3 n plus 4 divided by 5 multiplied by 4 and a 3, which is equal to n minus 3, n minus 1, n plus 2, n plus 4 divided by 5 factorial and a 1. So now substituting all these values of a2, a3, a4, a5 in the equation in the general solution as we have discussed above, so we can get y of x is equal to a naught plus a 1x plus a 2x square plus a 3x cube plus a 4x 4 in the general solution as we have taken for the by power series method, as we were taken y is equal to summation m is equal to 0 to infinity am x power m. So we can write the series like in the form of this, and now substituting the values in this equation, a1 in place of substituting the values of a1, a2, a3, a4, a5 and arranging, so we can get this in the form of this is 1 minus n into n plus 1 divided by 2 factorial x square plus n minus 2 n n plus 1 n plus 3 divided by 4 factorial x power 4 plus up to so on. This is a naught plus a 1 x minus n minus 1 n plus 2 divided by 3 factorial x cube plus n minus 3 n minus 1 n plus 2 n plus 4 divided by 5 factorial x power 5 plus up to so on. So this implies that y of x is equal to n naught y1 of x plus a1 y2 of x, which is the general solution as we have discussed in start. So this is the value of y1 and this one is the value of y0. So this is the general solution of the Legendre differential equation. See you next time.